Hey everyone, it's Jason, and I'm going to try and answer the question, can you correct white balance in JPEG? So if you're shooting in JPEG, can you correct white balance? Now, everyone kind of already knows the answer is no, but I wanted to sort of research this question a little bit more and see exactly what does that mean? Does that mean if you try and correct white balance in JPEGs that the result's going to be ugly? So I wanted to try and quantify this a little bit. So what I did was, first of all, I wanted a algorithm that could tell me just visually how far a corrected image is from an ideal image. There are many different algorithms actually that can test or measure the difference between two images, image similarity indices. And what I did is, as you can see on screen, is I took some images of mine and I sort of modified the tint of them. I did that several times, and I modified the white balance of these images, and I tried to determine how far they were away from the original image by using these similarity measures. So here I used 3 calibration data sets. One from this common gallinule, and we've got this ring-billed gull. And I ran these tint-changed images through different image similarity indices. And so there's actually a Python package that I use to do that. So you can see here, oh, not there, that's some results I'll show you later. You can see here in Sublime Text, I wrote a Python program to do this. Now, this Python image similarity measure library, you can get it, I think, in PIP or whatever. It has 1, 2, 3, 4, 5, 6, 7. It has 8 different image similarity measures: FSIM, ISSIM, PSNR, RMSE, SAM, SRE, SSIM, UIQ. Some of these algorithms performed very poorly. For example, FSIM didn't work very well to capture great differences in certain cases. Some of these algorithms, like ISSM, gave 0 because I think they actually don't take into account image hue or image tint changes. The finalist algorithms were PNSR, RMSE, SRE, SSIM, and UIQ. I paid careful attention to the difference in magnitude changes between different images and how these algorithms performed, and some of them didn't measure tint changes as well as I would have liked. To actually make a long story short, the finalists for measuring the difference in tint changes were RMSE and UIQ, which was kind of interesting because actually, in another test, in an article I'm writing for Photography Life, actually, I determined that UIQ was actually the best image similarity index that could be used to determine how well noise reduction works, or how noise affects an image. The more noisy an image, the worse it looks, or maybe the more noisy an image, the more the image quality is affected. So UIQ was the best algorithm in that case for determining the deviation from an ideal when it comes to noise. And RMSE, or root mean square error, was actually the worst algorithm. Not the worst, but one of the worst algorithms for determining the degradation due to noise. But in case of tint, root mean square was actually a pretty decent algorithm. Only root mean square and UIQ were the best algorithms to determine the difference between different images. So in this video, I'm using root mean square error because it performed a little bit better than UIQ, but I think UIQ, Universal Image Quality Index, which was actually an algorithm published in 2002, could also be used, and that I think UIQ is generally one of the best image similarity algorithms when it comes to doing things like numerical measures for photography. Yeah, so root mean square error is what I'm using now, especially because it's faster, much faster to compute than UIQ. So basically, I wrote a simple Python program to measure the deviation from an ideal original. So what I did is, you can see, I took a picture of myself. Let's see the picture of myself here. Yes, this is a picture of me in my younger days. And I successively increased in RAW. So this image comes from a RAW file. I successively increased the white balance of this image by 200 points, 200 kelvins each time. So you can see we were starting at a kind of normal white balance, It gets successively warmer. See, it's getting successively warmer. And as you go down, you can see the image gets quite warm. So these images have successively worse white balance. Now, what happens if you try and correct the white balance in a JPEG? So basically, I exported all of these JPEGs, and then I tried to correct the white balance based on the neutral gray background in the exact same way for each of the images. You can see now, here's the result. Okay, so this is 0. Now this image corresponds to an increase of 200 kelvins. And as I keep increasing 200 kelvins, you can see that actually the white balance correction is pretty good. But notice that in the cheek area here, the skin is getting a little bit of a cyan tone. And as I keep going down, you can see that cyan tone kind of increase very slowly. Okay, so now we're at like 30 images, which is 30 times 200 or 6,000 Kelvin. So a 6,000 Kelvin correction is, you can see that there's a noticeable increase of a kind of bluish cyan tone in the highlights of my skin. Now that's generally what's happening. So at that level, the white balance correction is pretty off. So it does prove that correcting white balance in JPEGs, especially if the white balance is very distinct from the actual white balance, is not a good idea. But look, I actually ran all of these images through root mean square error. And the blue, so look at this chart here. Just look at this chart. The blue dots correspond to the root mean square error of the uncorrected JPEG images. So you see that, and the root mean square error for a given image size is essentially proportional to the Euclidean distance from the image to the ideal image, from one image to another. So it's equivalent to the Euclidean distance. This graph kind of makes sense, and it kind of corresponds to what our eyes see too, I think, because at first maybe a 1,000 increase in Kelvin is noticeably more orange, but as you get higher and higher, it just starts to get more and more orange. But anyway, the red dots are the root mean square error after correction. So you see that the correction does bring the image, of course, very close to the original. And if you look at the difference between, say, this image, which is just 200 kelvins, and this image, which is like 1400 kelvins off but corrected in JPEG, there's not much difference. There's a little, you can see the cyan tone already. And in my opinion, I think that the white balance correction in JPEG doesn't look so bad as long as the difference between your ideal temperature and your actual temperature is not more than 1,000 kelvins or so. You're still going to lose some fidelity, image quality, but somewhere in this 1,000 range, you're not going to lose too much image quality. After you go past 1,000 Kelvin difference, then correcting white balance in JPEGs is a little worse. And but that, even these very horrible images can actually be corrected. So let's say I take the image that is like 6,000 kelvins off. I can actually go into Darktable and correct that thing. I can correct it a little bit more by using the RGB curve independent channels, or any raw developer. You just go to the curve tool and use independent channels. When you do that, you can actually correct a lot of that cyan look in the highlights. You can actually see what happens. Let me display the histogram for each of these images. If I display the histogram, you see, not the histogram, if I display the waveform. If I display the waveform, look at this waveform here. Look at the reds, basically. So if I go through the images, you can see that the process of taking a JPEG in the wrong color temperature and correcting its white balance, what's happening here is that it's crushing the reds. It's crushing the high end of the reds. The rest of the image data is relatively unaffected, but the high end of the reds is affected, and you can see it's being flattened. So I could go into Darktable, I could go into the tone curve, the RGB curve module, and sort of edit the red channel to somewhat simulate a more corrected image. Now that's not really going to bring back the image quality. Even if I do this basic adjustment, the tint of the corrected image at like 6,000 Kelvin off is still going to be pretty bad in my opinion. So bottom line is the following. If you shoot in JPEG and you attempt to correct white balance, corrections can work if your color temperature is not too far off from your target temperature. For example, if you're just under 1,000 kelvins off, you can probably make a pretty good correction. Once you start to go up, the top end colors will be affected first. The farther you go past 1,000, the more uncorrectable it's going to be. So, of course, that's another reason to shoot in RAW. But it's an interesting test anyway. Actually, white balance correction in JPEGs doesn't look that bad. In some cases, say you're just 300 kelvins off. Well, a white balance correction in JPEGs won't be that bad. But a white balance correction, if you're 2,000 or 3,000 kelvins off, then you're going to start to see some problems in those high ends. If you want to correct white balance in JPEGs, just be aware of the limitations. I wouldn't say don't do it at all. If you only have JPEGs, you can correct it. And if you do some extra work, like playing with some independent channels of some curves, then you can actually get the image looking kind of decent, but it won't have the image fidelity of the original RAW file. So yeah, hope you enjoyed this video. Don't forget to subscribe and give it a like, and I'll see you again next time.